Okay.
Okay, hi everyone. So welcome to our SPD seminar today. So today we will have Yier Lin from Columbia. He's a fifth-year PhD student with Ivan. So we're happy to have you here and look forward to your talk on the short-time large deviations of the KPZ equation.
Okay. Thanks, Karsten, for the nice invitation. And today is a great pleasure to talk about our recent work on short-time large deviations of the KPZ equation. So this is a joint work with Li-Cheng Tsai from Rogers, who is also in the audience. So let's just start. So what is a KPZ equation? Introduced by Katzav and Zhang in 1986, it's a nonlinear stochastic PDE given by the following form, with C to be the space-time white noise. So it's a very nice model for the random interface growth, where you can view this H as the height function of some random growing surface, where T represents the time and X represents the location. So X is one dimension. So the growth of this surface is governed by this stochastic PDE, where C plays the role as the driving force in a random environment. And the Laplacian corresponds to some smoothing mechanism, which gives your surface certain regularity. And the nonlinearity term here, what basically tells you the growth of the surface is slope dependent. So this is a very brief physics philosophy behind the KPZ equation. So mathematically, the first thing we want to understand is how to make sense, how to understand the solution, so how to define the solution theory. So the KPZ equation, the solution theory, it's not well posed in the classical sense, because if you first ignore this nonlinearity term, what you have is a standard heat equation plus the space-time white noise. Then a simple calculation will tells you the regularity of the solution should be like a Brownian, motion, so it's Holder 1/2 minus. Then when you look at this nonlinearity term at here, because you have this Holder regularity 1/2 minus, you take the partial derivative, what you get is a distribution. And the problem is in the classical, so you do not know how to make sense of the square of this distribution here. So one way to make sense of the solution theory to the KPZ equation is instead we first look at a different stochastic PDE called the stochastic heat equation, or in abbreviation SHE. So this is a linear stochastic PDE where the solution theory can be formulated in the mild sense, or in the Duhamel sense. And the solution theory is well posed, which means the solution exists and is unique. And also, the solution of SHE will preserve the positivity, which means if you start our SHE from some positive initial data, then with probability 1, the solution remains to be positive at any time and space. So what's the relation between the KPZ equation and the stochastic heat equation? So you look at the KPZ equation at here. So this C is the space-time white noise, so it's a random distribution. But formally, you treat it as a nice and regular function, and you consider this exponential transform of H. Then, if you look at the temporal derivative of Z, it's like you're computing the temporal derivative of this exponential of H. So apply chain rule, and using this relation, you'll find out, formally, this Z will solve or satisfy the stochastic heat equation at here. So one way to define the solution theory, to define the solution to the KPZ equation is we first take the solution of stochastic heat equation. Then we apply the logarithm by this formal transformation. So we'll call this notion of solution, so define it to be the logarithm of the stochastic heat equation, the Hopf-Cole solution to the KPZ equation. And you can see this definition indeed makes sense because of the positivity of the stochastic heat equation. This Z is always something positive, as long as you start from some positive initial data. So that you can take the logarithm. So actually, there are other equivalent ways to define the solution to the KPZ equation. For example, you can use the theory of a regularity structure. But in the context of this talk, I would just stick to this notion of Hopf-Cole solution. And like one advantage is like you can study the KPZ equation from your knowledge of stochastic heat equation, which is sometimes like more manageable. Okay, and you can also look at the KPZ equation starting from different kind of initial data, and the initial data that we'll deal with in this talk is the narrow wedge initial data. So this narrow wedge initial condition is not directly defined for the KPZ equation, but instead you look at the stochastic heat equation and you start it from a Dirac mass at 0. Okay. So the reason like why we call such initial data for KPZ to be narrow wedge, it's because like when we start from this delta mass, when time is really small, like the solution can be approximated by a heat kernel. It's like you solve this equation without the noisy term. So it's just a heat kernel. Then it tells you when time is really small, the KPZ equation is approximately this logarithm of the heat kernel, which is basically negative x squared over 2t. And so it's a negative parabola. And when time becomes really small and small, you'll see this parabola will become narrower and narrower. So this is why we call this the narrow wedge initial data, okay, for the KPZ equation. So thinking of your solution, your h describe the height function of some surface growing from this narrow wedge. A natural question to ask is how fast this like surface grows, and how about the fluctuation around its typical value. So in the work of Meerson and Costel in 2011, they show that if you look at the long time asymptotic of the 1-point fluctuation for your KPZ equation, the fluctuation is of order t to the power 1/3. So take t goes to infinity. And the fluctuation limit turns out to be the Tracy-Widom GOE distribution. If you're not familiar with that, so it's a random, it's a distribution, or originally comes from the random matrix theory, where GOE represents the Gaussian unitary ensemble. So maybe the only thing to know about this Tracy-Widom GOE is it has a PDF look like this, with the left tail decay super exponentially with tail exponent 1/12x cubed. Okay. So this is the fluctuation limit for the long time behavior of the KPZ equation. On the other hand, if you look at the short time behavior, which means you let t goes to 0, then the KPZ equation, the typical value will become this minus logarithm root 4 pi t. And to see the fluctuation, you will need to multiply the numerator by a very big number, which corresponds to 1/t to the power 1/4. And the fluctuation limit is given by this Gaussian distribution, okay, with variance root pi over 2. So these are basically the fluctuation limit theorem for KPZ equation in long time and short time asymptotic. So like in the case of ID random variables, there are 3 basic questions: law of large number, central limit theorem, and the large deviation. So like for the KPZ equation at here, basically the first 2 questions is answered because of these results, both in long time and short time regime. So the next question to ask about, the natural question to ask about is like, how about the large deviation when you send t goes to infinity or t goes to 0? So as you can see from the title here, like in this talk, we're going to deal with the large deviation of the KPZ equation in the short time regime where we send t goes to 0. So in this regime, like the result, so like which has been less mathematically treated, I would say. But before that, let me first review a few results like about the large deviation for this KPZ in the long time regime. Okay. So what is this large deviation really about? Like for the KPZ equation as time goes to infinity, for example, you can look at the probability of the following event where you look at this h plus t over 12 to be smaller than negative lambda t. So look at the lower tail probability. Because of the fluctuation limit theorem, we know the typical value of this h plus t over 12 like is 0, and the fluctuation around 0 is of order t to the power 1/3. So as t goes to infinity, this probability will just goes to 0. But the large deviation really tells you how fast this probability goes to 0. Actually, it's a result first proved by Li-Cheng and also by Katzav 1 year later using a different method, where they show that this probability, as you let t goes to infinity, will decay exponentially, with speed t squared, and with some rate function on the right-hand side given by phi lambda. The rate function turns out to be explicit, though I do not show it here. But the interesting phenomenon is when you look at the asymptotic of your rate function, when let lambda goes to 0, the rate function will behave asymptotically as 1/12 lambda cubed. On the other hand, if you let lambda goes to infinity, the asymptotic of the rate function will become this 4/15 pi lambda to the power 5/2. So let me first explain this 1/12 lambda cube asymptotic. It's not something very surprising because this exponent should just follows from the left tail exponent, so the lower tail exponent of the Tracy-William GUE distribution in our fluctuation limit regime. Okay, so when you look at the tail behavior for this H, near the center, which means lambda is close to 0, you're still in the fluctuation limit regime. But the interesting thing is when you go very deep in your lower tail, where you consider this lambda to be very big, you'll see some new regime, this 5/2 power law will appears, and it does not follow from your fluctuation limit. Okay, so this implies there's a crossover, or phase transition happen when you go from when you look at the position in your tail, from near the center, which is in the fluctuation limit regime, to some new regime. Okay, so I also want to mention that such crossover from qubit power law to the 5/2 power law was actually proved proved earlier in the work of Ivan and Promit in 2018, where instead of looking at the large deviation regime, so where we send t goes to infinity, so they consider the time to be very big. Okay, so time to be finite but large time t, and they're able to establish a tail bound for this lower tail probability, which identifies such crossover. Okay, from qubit power law to the 5/2 power. And for the large deviation, you can also look at the upper tail probability. For example, you can look at the probability where h plus t/12 to be greater than lambda t. And actually, such large deviation was established in the work of Tsai and Li-Cheng last year. And for the upper tail, you will not see it any crossover. Okay, so going back to this 5/2 power law, actually, such phenomenon was first predicted in a physics work by Kolokolov and Korshunov in 2007. Actually, their prediction is following. So their prediction is if you take time to be very small and you go very deep in your lower tail, which means you take lambda to be very big and you take t to be very small, then you will see this 5/2 power law arise. But what has been proven now mathematically, are the behavior for this 5/2 power law is only for t to be very big, either finite large t or t goes to infinity. Okay, so basically our motivation is twofolded. First, as we mentioned before, we also have a fluctuation limit theorem for the short time regime. So it is natural, we want to establish a large deviation principle for that. And the more important thing is we also want to look at the lower tail rate function, and we want to see if there's some crossover happen, when you look at tail near the center, to the very deep lower tail. And in particular, do you indeed see this 5/2 power law appears in your lower tail rate function in the short time large deviation regime? Okay. So this is our main result. So jointly with Li-Cheng, so we established the first rigorous large deviation principle for the KPZ equation, in the short time regime, where that time goes to 0. so which corresponds to look at the following probability. So either h plus this typical value, this negative log root 4 pi t, greater than a fixed value lambda or smaller than negative lambda. So basically, like the large deviation tells you this probability will decay exponentially with speed 1 over root t, and with the rate function given by like some like phi plus or phi minus, depending on whether you're looking at the upper tail or the lower tail. So these rate functions are in a variational form, but like we are able to extract, so look at the lower tail rate function, we're able to extract the asymptotic. So where shows that if you take lambda goes to 0, then this rate function behave asymptotically as 1 over root 2 pi and lambda squared. While you take lambda goes to infinity, the rate function will behave asymptotically as, so you will see this 5½ power law indeed arises. So this 1 over root 2 pi lambda squared, again, it's something followed from the fluctuation limit theorem, because if you remember, in the short time fluctuation limit theorem, like our fluctuation limit is Gaussian. So this tail exponent is nothing but the tail exponent for that Gaussian random variable. The interesting thing is, like, you again see this 5½ power law. You see a crossover from the Gaussian regime to this 5½ power law again, and you will see this constant, this 4 over 15 pi, like in your limit, just coincides with this 4 over 15 pi in the large deviation for KPZ equation in the long time regime. Okay, so you can also ask, like, what happens, like, so basically I explained the asymptotic for the lower tail rate function. You can also ask what happens for the asymptotic in the upper tail rate function about this phi plus. So in particular, okay, you can also show if you replace this phi minus by phi plus, when lambda goes to 0, you will have the same behavior as here. But when you let lambda goes to infinity, like actually, like it is conjectured that you will see this 3½ power law. Okay, so like I will pause for question. Like, is this brief introduction and the main result clear?
Why is the result only for certain positive lambda? I mean, it's so is this not is this limited result or is kind of a trivial to see the other side of the lambda? Lambda.
Yeah. So basically, if you take t goes to 0, this h plus logarithm itself will just goes to 0. So if you take lambda to be negative, then this probability, for example, you look at this lower tail probability, this will just probability will just goes to 1 because the typical value of h plus logarithm is 0. Like, is that the question you asked?
That's okay. I'll try to sort out because I'm going to present more results, so I'll try to sort out later. Thanks.
Yeah. So in this talk, I will just focus on explaining like how to prove this 5½ power law arise like in the lower tail rate function. Both because like it is more interesting because it's a phenomenon outside the fluctuation limit regime, and also because the proof it's much more difficult. Okay, and before that, I want to mention actually there are a few physics prediction or heuristic like exist like which predicts the result about like the asymptotic for this rate function. For example, like first in the work of Kolokolov and Korshunov in 2007, where they predict this 5½ power law in the deep lower tail, and also like 2 works in 2016, like first is by Doussal, Majumdar, Schehr, Rosso, and the second is by Kamenev, Meerson, Sasorov. So both results predict the exact asymptotic for these limits. Okay, and like we'll first explain the heuristic. So like before presenting our rigorous proof, we'll first explain the heuristic, which is called the weak noise theory, like taken from the work of Kamenev, Meerson, Sasorov. So the reason is first, it's a very interesting heuristic, and The deeper reason is actually you will see this heuristic, it provides a very nice input for our like rigorous proof of the 5 half-power law. Okay, so we'll first take a little bit of time to talk about this heuristic. So what is this heuristic or the weak noise theory really about? So first, like we consider a different scaling regime. So at the beginning, we're looking at the short time regime where we take time goes to 0 and study the 1-point large deviation. So now let's consider this h epsilon. So we scale in this way. So basically, this h just satisfies your original KPZ equation, and you now consider h epsilon. And because it's a simple scaling, you can find out this h epsilon will also satisfy a rescaled version of KPZ equation. So now every term remains the same except like in front of the white noise, you get an extra root epsilon. Okay. So like we will take epsilon goes to 0. So this is why like the theory is sometimes called weak noise theory, because it just corresponds to the noise becomes like weaker and weaker. And so this physics heuristic, it's just composed like of 2 steps. So first, like it derives like it study a functional large deviation of this h epsilon as epsilon goes to 0, so on some space-time domain. So in other words, it take epsilon goes to 0 and satisfy and study the large deviation of the trajectory for this h epsilon as a space-time function. Then having that large deviation, you can immediately push it forward. So using contraction principle, you can push it forward to the 1-point large deviation of this h epsilon at time 2 and space 0. So heuristically, you can get a large deviation for this h epsilon with the rate function. So because of you're pushing it forward, it can be expressed in terms of variational expression. And to understand like the rate function, in particular the asymptotic, when you look at the deep lower tail, you need to like solve a Hamilton variational problem. Okay, so basically these 2 steps like heuristically will give you the asymptotic of this 5 half-power law. But you might wonder like what does this like why this is related to the short time regime. So now we're looking at a different regime which corresponds to we send epsilon goes to 0 instead of time goes to 0. So here's the fact, because like you have this scaling, like it is not hard to see if you can establish the 1-point large deviation for this h epsilon, which corresponds to like this weak noise scaling. You send epsilon goes to 0 like for a fixed time and space level. Like it is equivalent to show the large deviation like for your original KPZ equation in the short time regime. Okay. So like you only need to like study the 1-point large deviation for this h epsilon as epsilon goes to 0. Okay, so let me explain first how to derive a functional large deviation. So like these are just like at the heuristic level. So first, like you look at your space-time white noise multiplied by root epsilon. So it's some well-known result will tell you the probability of this space-time white noise times this root epsilon to stay around some L2 function. So you consider certain topology because this space-time white noise is a random distribution. The probability of this will decay exponentially with speed 1 over epsilon. And the rate function is given by this 1 over 2 square of the L2 norm of your rho. Okay. This is basically the large deviation for space-time white noise. Then you're wondering what is the probability, like what is the functional large deviation for h epsilon? In other words, what is the probability for this h epsilon to stay around like this trajectory h? But formally, this KPZ equation will tells you this probability should be like same as looking at the probability of your space-time white noise multiplied by root epsilon to stay around the red quantity on the right-hand side. As you just plug in your trajectory h in the left-hand side like here. Okay, so because you have the large deviation for this space-time white noise, basically you obtain a large deviation for this space-time trajectory for the KPZ equation. Okay, you'll have the same speed 1 over epsilon, and the rate function is given by like this L2 norm here. So now you have obtained a functional large deviation principle for this H epsilon. But the thing you want to understand is like what is the 1-point large deviation? So this just corresponds to applying contraction principle because you know the information about your trajectory, and what you need to do is only to like pin the value to look at the value of the trajectory at time 2 and space 0. So basically, like applying contraction principle, you can get the rate function. So what is the rate function? The rate function turns out to be the infimum of this object, of this like where rho is just related to h like by this equation. So basically, it's the infimum of this object where you consider different kind of h, as long as because it's the trajectory of your KPZ equation, so it needs to satisfy this narrow wedge initial condition, as well as like the value of this h at time 2 and space 0 need to pass this negative lambda, because we're looking at the large deviation like near this negative lambda. Okay, you're trying to minimize. It turns out that you're trying to consider the infimum, or you're trying to minimize this functional over the trajectory, subject to like the condition that your h satisfies the narrow wedge initial condition, and also like h20 equal negative lambda. Okay, so basically, like if you're doing like if you're trying to find out the minimizer of a one variable function, what should you do? You should just take the derivative and find out like where your derivative is 0. But here, like you're not in the one variable case. Actually, your variable is a function. So there's like some generalized version of the calculus. So basically, you're dealing with the infinite dimensional case. So basically, you can use calculus of variation, which will tell you if h is the minimizer of this minimization problem, you need to satisfy some PDE. And the PD is given by, if you like denote rho by the right-hand side here, so the PD is just given by the first line at here. So I'm saying for h, which minimize this functional subject to certain boundary condition, it needs to satisfy a PD, which is given by the first line at here. And actually, it's a pair of PD between rho and h because so this is an like artificial like relation because we set rho to be this on the right hand side. So basically, like we want to solve a pair of PD between rho and h, and presumably if we can solve it, then like if you like you can find out the solution. I mean, then like you plug in inside this expression, compute the L2 norm, you should get the rate function. Okay, so this is the heuristic. But it turns out that if you look at this pair of PDE, like it's quite hard to find out an explicit solution. And also, like our goal is not really to understand like what is the solution for this pair of PDE, because what we want is really to extract the asymptotic for this rate function as lambda goes to infinity. Our goal is not to find out the value of phi minus lambda for each lambda. We're interested in the asymptotic when lambda goes to infinity. Okay, so this amounts to like you're trying to extract the asymptotic. So basically, you'll take lambda goes to infinity, and a natural thing to do is now you apply some scaling to your h and rho, like in your pair of PDE. Then under this scaling, like your h and rho, so like will satisfy every scaled pair of PDE. So basically just plugging the scaling inside this pair of equation, you'll get basically every term is the same, except in front of the second order derivative at here, you'll get an extra like 1 over 2 lambda. Okay. So like our goal is really to understand like how the solution behave as lambda goes to infinity to this pair of PDE. But like at the heuristic level, it is natural to guess to believe that if you take lambda goes to infinity, the solution for this pair of PDE will converge to the pair of PDE where these second order derivative term just vanish because the coefficient in front of them goes to 0. Okay, so in the asymptotic, so the asymptotic of your rate function really corresponds to the solution of this pair of PDE, of this pair of PDE where the second order derivative just vanish. And you're able to find out like one solution for this pair of PDE. Like in particular, you can find out one explicit rho star, which and corresponding H, which solve and this equation, and it's given by the following form at here. So this L function is something explicit, though I will not present the form at here. But maybe the only important thing is first the L2 norm of your rho star, which corresponds to the solution, is given by this 4/15 pi. On the right, and maybe one other thing we may use later is if you look at this this expression. So this rho star is supported because of this indicator, and it's supported in some length shape where your LT is some curve starting from 0 and end at 0 when you go from time 0 to time 2. Okay. Then because we have this solution and the L2 norm is given by 4/15 pi, you can guess that. So the heuristic just tells us you'll expect this phi minus when lambda to be very big will behave asymptotically as 4/15 pi lambda to the power 5/2. So where is this lambda to the power 5/2 up here? So here we have the matching constant in the asymptotic limit, but this lambda to the power 5/2, it just corresponds to the scaling. Because if you remember, what is this phi minus corresponds to? It corresponds to the L2 norm of this rho, which solves this pair of PD. But when we take lambda goes to infinity, we have applied a scaling at here, where we change rho to this lambda rho. So we have certain scaling, and if you compute the square of the L2 norm of the right-hand side, so what this is, so you will have an extra lambda square coming out because you're taking the square of L2 norm, and by a change of variable, so you replace x by lambda 1/2 times x, you'll get an extra lambda to the power 5/2. Sorry, you'll get an extra lambda to the power 1/2. So altogether, you'll get lambda to the power 5/2 up here. Okay. So this is basically the heuristic why you would expect this 5/2 power law appears. But actually, there are certain problems with this physics heuristic. I mean, from the point of view of mathematics, the first thing is why you can remove the viscosity. In other words, why indeed you would expect the solution to this pair of PDE, with the second order derivative, really goes to the solution for this pair of PDE without the second order derivative, as you take lambda goes to infinity. And the other problem is, so you find out a solution for this pair of PDE, but in general, for this kind of Hamilton-Jacobi equation, there are infinite number of so the solution is not unique. And what you really need to do is you look at all possible solutions of this rho and H, then you compute their L2 norm and find out the smallest one among them. So there's also the problem of uniqueness, and also when you do the argument at here, in general, you just apply you just assume everything is nice enough, which means H is just very smooth and nice object. But H, it's actually the trajectory of the KPZ equation, which is in general have the same, for example, spatial Holder regularity as a Brownian motion. So you also need to take some effort to make sense how to interpret these derivatives, because H actually it's something Holder 1/2 minus. So actually,
very quickly, a question regarding informal the previous slide.
Right here.
Yeah. So this equation, the So you look at the first two lines of identities, the equation. So this is endowed with initial terminal value problem for your. I'm reading it. Perhaps that's for your. Is that for your rho or for your h? The terminal value.
The terminal value.
And the terminal. I mean, for t equal to 0 versus and also the t. You have a point to start and you have a point to hit, right? When you do the calculus variation a few slides ago. So yeah, so you have a one is an initial value, that's where you start. The other has to do with this h epsilon 20. So that should serve as a terminal value, I guess. That's where you end up with, right?
So actually, like you also need to impose like certain boundary condition, like when you do this calculus variation. In particular,
so that's your you said boundary h20 equal to minus lambda.
Yeah, and actually you also need to set your rho like at 20 to be a delta function, which I like to not show you.
We're prescribing if you can only have two boundaries.
Actually, your h also needs to satisfy the boundary of the KPZ equation, because h is the trajectory of the KPZ equation, so it's a narrow wedge.
Okay, so my question is going back to your equation, how do you go to verify the next line h star? I think you used h star or rho star. Where does the initial terminal conditions come in here?
So the terminal condition, okay. So I did not show the solution h here, but actually for the terminal condition of rho, like as I mentioned, like when doing this calculus of variation, you need to impose this rho to be a delta function at time 2. So basically, at time 2, rho is a delta function, like with the mass at 0. So basically, like this formula just tells you indeed it satisfies this boundary condition, because if you look at the form of LT is something like goes to 0 when t goes to 2. So basically, given this expression, you'll see like outside. So outside this support, so when x is like away from 0, like the value of rho is just 0, and like at 0 it's just a delta function.
So this is a direct verification. So you can guess what the rho star is, and then you plug it in. Is that how?
Right. Right. So like I just tell you, like this is one solution. So as I mentioned before, like so the way the physics heuristic works is they find out one solution, like using certain method, but like you cannot argue this is the only solution.
Thank you.
Okay. Thanks for the question. So like what is our approach? Actually, like our proof it's very different from the physics heuristic. So we start working at the level of stochastic heat equation. So instead of directly look at the KPZ equation, like we start from stochastic heat equation, and we first prove a functional LDP for that. Then immediately again you can push it forward, so by taking the logarithm and restricting at one point to the KPZ equation. And now, okay, this rate function is still in a variational form, but so like in terms of Feynman-Katz formula, you will see. But the nice thing is you can avoid like these issues that arise in the PD argument, and you're able to apply certain probabilistic argument to prove this 5-half power law, like in the asymptotic. Okay, so the rest of the talk will just be devoted to that. So we'll first explain how to get a functional LDP for the stochastic heat equation. So basically, instead of looking at this h epsilon, you look at exponential transform of it. So look at the stochastic heat equation under this weak noise scaling. So like here, it's just something formal which tells you why we'll expect the trajectory of stochastic heat equation will satisfy certain large deviation, like with the rate function given by the red line at here. So basically, if you formally applying Feynman-Katz formula, because okay, this C it's not a function, it's a distribution, but you just treat it as a nice function, you can apply Feynman-Katz formula to represent the solution as the following expectation here. Okay, so this B, this capital B, lowercase b, it's just a Brownian bridge. Okay. In the Feynman-Katz formula, you have a Brownian motion, but this is because you start from the Dirac mass, so it's like the Brownian motion will become the Brownian bridge. And this expectation, okay, the Brownian bridge will go from 0 to x, and this expectation like only acts on the Brownian motion. So the randomness of the space-time white noise is preserved. Okay. So the formal way to derive the functional LDP of stochastic heat equation is consider this expression and consider it as so let me denote the right hand side as the as J rho. Then like this stochastic heat equation, you just like replace this rho here by the root epsilon c. It's just like J root epsilon c, right? So we know like for space-time white noise, you can multiply by root epsilon, it will satisfy a large deviation principle. So at the formal level, you can guess the large deviation of the trajectory for your stochastic heat equation can just be obtained by you push forward the large deviation of the space-time white noise under this this map J. Okay, and by formally applying contraction principle, you'll just see like you can just guess that maybe the stochastic heat equation should also satisfy a LDP with the same speed, this 1 over epsilon as the large deviation for the space-time white noise, and the rate function just given by the following form. So it just comes from formally applying the contraction principle. And this is indeed the case, though this is not a proof. The problem is because like this J root epsilon c is something like, first, this map is not a continuous map from the space-time white noise to the trajectory. And actually, like given the expression at here, it's only a formal expression because c is not a real function. It's a distribution, right? But like actually we can prove indeed like the stochastic heat equation will satisfy such large deviation. The idea is actually you can if you look at this formal expression, you can make sense of it in terms of an chaos series expansion, which corresponds to like you Taylor expand this exponential at here, then okay, for the series in your Taylor expansion, you interchange the expectation and the stochastic integral, and the integration. So basically, you can expand the stochastic heat equation as infinite sum, where the case term in your summation is just a k-fold stochastic integral, where this p is some deterministic function, like given by the product of your heat kernel from the Brownian bridge in your Feynman-Katz formula. Okay, so the point is now we can express the stochastic heat equation in terms of infinite sum, where the case term is just a k-fold stochastic integral. And a theory like of Martin Heyer and Hendrik Weber, where they derive actually a general large deviation principle for the something called Wiener chaos. But by certain application, you are able to derive the large deviation of this finite summation, and with certain rate function at here. So you can see the rate function is also like in the form as you formally applying contraction principle, like from space-time white noise to this trajectory under this map like IK. But like what we want is actually the functional large deviation of the stochastic heat equation, which is this like infinite sum, right? So it really corresponds to you want to derive the large deviation for this infinite sum from this finite summation. And this amounts to showing some exponential approximation, which corresponds to like you look at the difference of this infinite summation and finite summation when you take n to be very big, and to show okay their difference actually is very small, but it's not just going to zero. It's going to zero very fast, like in an exponential like speed, or something like that. And so like there are a lot of details like I just omit, but like one important input is you need to understand certain tau estimate for these like multi-stochastic integral, not just at the 1-point level, but at the functional level. So what I mean at the functional level is you really consider this as some space-time function, and you take the norm, you look at the tail behavior. Okay. So Now, how to derive the functional tail estimate? So a brief explanation is, okay, you first look at the one-point tail estimate for this stochastic integral, and you have some tool called hypercontractive inequality, which basically tells you for these multiple stochastic integral, you are able to prove a uniform tail bound for this ik, which is uniformly like in k, and the tail behavior of this ik only depend on two things. First, like it's the how many fold your stochastic integral have, so this number of k. The other thing is like what is the variance, what is the second moment of this ik. Okay, so basically like you can get a one-point tail estimate for the stochastic integral, and now like you need to apply certain Kolmogorov type of argument, which lift the one-point estimate to the functional tail estimate. Okay, so there's like quite an amount of detail in that. Like I don't really want to talk about that, but basically like when you have the exponential approximation and with a few other ingredients, you can show the functional large deviation for this infinite summation, which is a stochastic heat equation, to be the following format here. So basically, you just replace this n here with infinity. Okay, so this is the form of your rate function. And what is this infinite summation corresponds to? So actually, in the case of, you look at this infinite sum, when you have this space-time white noise inside, the infinite sum just it's just a solution to the stochastic heat equation. So when you replace this root epsilon c by a deterministic L2 function rho at here, this turns out to be also to be a solution, but the solution to a deterministic PDE, where you replace this root epsilon times c by the L2 function rho. So then you apply the Feynman-Katz formula. Actually, it tells you this infinite summation is nothing but the expectation on the right hand side. Okay, you can also see like where this comes from by just tail expanding the exponential function and apply the interchange the expectation and the integral in Fubini, and you'll see like this comes. So the thing I want to tell you is, okay, you can get a functional large deviation principle of this trajectory of stochastic heat equation, and you can express your rate function here, like in terms of some expression of Feynman-Katz representation. Okay, so this is like our result for the functional large deviation principle. So basically, like you can express like the rate function in terms of like this infimum with respect to the Feynman-Katz. Okay, so I hope I did not like lose your O. But then the next step is immediate. You have a functional large deviation for the trajectory. Then what you do is you just take the logarithm and fix the time to be 2 and space to be 0. You apply contraction principle. Then because the logarithm of z it's h, and the logarithm of heat kernel at time 2 and space 0, it's just logarithm of root 4 pi. So you immediately get a large deviation principle for like 1 point LDP for your KPZ equation. Like under the weak noise scaling, so as epsilon goes to 0, you'll have a large deviation with these two rate functions, as I mentioned before, like in a variational form. So basically, we have established the 1 point large deviation for the KPZ equation in the weak noise regime, which is equivalent to the regime we considered at the beginning where time goes to 0. Okay, and we have an expression for the rate function. The more important thing, like you want to understand, as I mentioned at the beginning, is to understand the asymptotic for this rate function as you go very deep in your lower tail. So take lambda very big. You want to prove that you will see this 5 half-power law rise. So the first step, so now the tool we have is just this variational expression for the rate function. With an s, it's basically the logarithm of your Feynman-Katz representation. The first step you can do is something similar in the PD heuristic. You can apply a scaling rule like in the same way. And because again, you're computing the square of the L2 norm, So this scaling will help you factor out the lambda to the power 5 half. But at the cost of this scaling, your mapping S, which is this log of Feynman cat, will also be rescaled. Will be rescaled like, will just become this S lambda at here. So you can see now the goal is actually to prove this red line, because the goal at the beginning is to prove this asymptotic, but we have factored this 5 half power law. So you only need to prove this limit goes to 4/15 pi. So in general, this is not an easy question, because basically what you're trying to minimize is when lambda is really big, you're trying to minimize the L2 norm for your rows, satisfy this condition, satisfy this S lambda to be smaller or equal to -1. But it seems that this map does not tell you much information what kind of optimal row should be. But the nice thing, as I mentioned, is you have an input from this physics heuristic, which which is not of the argument, but this solution to the PD, like this row star, which I show you like a few slides before. So it is natural to guess, like when lambda becomes really big, which means when lambda goes to infinity, this row star should really be the minimizer, like for this infimum. Okay, and you'll see the L2 norm of row star is 4/15 pi, so you match with the limit at here. So to prove the red line at here, you only need to show two things. The first thing is this row star indeed satisfies the condition at here. So in particular, you want to show when lambda become really big, lambda goes to infinity, this S lambda row star will be smaller or equal to -1. In particular, we'll show it to be equal to -1. The other thing, actually, is harder. You really need to argue for any row satisfy like this condition as row lambda smaller or equal to -1, the L2 norm of row should be lower bounded by the L2 norm of row star. Okay. So, sorry, I will start from the first step, but actually, like in the meanwhile, you will see, like doing the first step will give you some idea of doing the second step. So, you want to compute this limit where this row is just something given, and the limit is basically the right-hand side, because this is the expression of S lambda. So as lambda goes to infinity, actually, if you're familiar with large deviation principle, this is actually something called a Varadhan's lemma, and the limit is given by a variational form again on the right-hand side. The reason behind is actually like you look at the large deviation of this Brownian bridge multiplied by a very small number, then like the probability of it to lie around a certain path x will decay exponentially, like with certain rate function given by this integral of like 1/2 x dot square. But when you compute the expectation, you will also have some exponential growth coming from this integral from 0 to 2 of this row star. So basically, when you're taking the limit, you're trying to find an optimal path, like of your Brownian bridge, go from 0 and end at 0, which like maximize this quantity. Okay, and you can like again. So for you want to find the optimizer, so you can again like use calculus variation. So you can transform. So you can find out the optimizer needs to satisfy the following Euler-Lagrange equation, which is an ODE. So I will not tell you how to solve this ODE, but I will tell you the class of solution, like all the solution to this PDE. First, it's not unique, and it's a one-parameter family given by this alpha L. So sometimes I will call this geodesic because you can also view this as a last passage percolation in a deterministic environment given by rho star. But it turns out that the solution or the geodesic is just given by this alpha times LT. So what is LT? If you remember, LT is nothing but the boundary of your rho star. And what I tell you is the solution is, okay, if you take this LT and negative LT, they're both solution. But if you multiply it by any like number between -1 and 1, they're also solution. Okay. And so if you want to compute the limit, you just need to plug in one of the geodesic or the solution like inside this equilibrium, and you will get it to be -1. Okay, so indeed you can show this limit will go to -1. But in the step 2, you'll see one important thing is for any, like for this class of geodesic, so as long as x equal to alpha times L, for any alpha between -1 and 1, this integral is always -1. Okay. So why this is helpful? So like I will skip a few lines because I'm like out of time. So remember, you're trying to show when rho satisfies certain condition given by here, when lambda is really big, the L2 norm of rho is lower bounded by the L2 norm of your optimized rho star. So this is the thing you want to show. And actually, okay, by certain perturbation of the Brownian bridge, and together with Jensen's inequality, you can tell that this condition will imply a weaker condition given by something like here. So this corresponds to perturb your Brownian motion into to the typical value given by x, then you apply Jensen's inequality. So then if you take lambda to be infinity and x to be your geodesic, so if you take lambda to be infinity at here, then this term will just be 0 and there will be no expectation. So it turns out that, okay, finally you're just dealing with the condition that you integrate the rho like here and subtract this integral at here, it should be smaller or equal to -1. The magic thing really corresponds to, at the beginning, you're trying to understand what is the L2 lower bound for rho satisfy this condition. So why it's lower bounded by the L2 norm of rho star. Where it seems hard to read the information from rho star given this condition at here. But now you're able to recover the information of your optimizer rho star, given this class of geodesic. So this is because, remember, we have this equation. When you replace x by any one of the geodesic, integrated will be -1. So if you replace the integral of this x dot square by this rho star, so where you do this replacement, you will see that the integral of rho subtract rho star, if you integrate along any one of the geodesic parameterized by alpha, you'll have it to be smaller or equal to 0. Okay. Then if you multiply this integral by certain function like 1 minus alpha square, you immediately get the second line. And then, okay, if you apply a change of variable by replacing alpha L to x, you can recover the information, the relation between rho and rho star. Actually, now the information will become the inner product between negative rho star and rho minus rho star is smaller than 0. So this really tells you, so from this you can immediately obtain using Cauchy-Schwarz, for example, the L2 norm of rho is lower bounded by rho star. Okay, so this is the idea. It seems from this condition there's no information of rho star, but actually the information of rho star can be recovered by this class of geodesic. Okay, so to summarize, we have proved so we first prove a functional large deviation of stochastic heat equation under weak noise scaling, and we push this large deviation forward to the 1-point large deviation of the KPZ equation. And so different from the physics heuristic, where there are certain issue appear in making sense the PD argument. So if you work at the level of stochastic heat equation and deal with the variational form of this 1-point wave function, you can apply probabilistic argument, and you can show actually there's a crossover from the lower tail rate function, from the Gaussian tail exponent to the 5½ power law. So I actually didn't tell you much about this Gaussian exponent, how to show it, but this is something comparatively simple. And in this talk, I only talk about the KPZ equation starting from the narrow wedge initial data. Actually, the proof also works for the KPZ equation starting from flat initial data, which corresponds to your initial data is just a constant 0. Okay, and you can also confirm the 5-half power law, like in the deep lower tail, which was predicted in the work of in the physics work by Kolokolov and Korshunov, and also Meerson, Katzav, Vilenkin, 2016. So one future question, then I will end, is actually you see that this 5-half power law, it appears both like for the KPZ equation, both in the short time and the long time regime, as long as you go very deep in the lower tail. Actually, like it seems it will also appear in some other models. For example, like in the physics work by Varadhan and the Leibowitz in 1998, you look at the TASAP, totally asymmetric simple exclusion process, like on a ring, and you look at some observable called the average time current, and you look at the one-cell tail behavior of that, you will also see this 5-half power law. So they have a physics heuristic showing that you'll see this 5-half power law. So one natural question is to ask, is this 5-half power really something universal, which does not only appear like in the tail behavior of KPZ equation, but also like for other models, like for example, in the KPZ universality class. Okay, that's my talk. Thank you.
Thanks, Yier, for this very interesting presentation. Are there questions from the audience? Maybe I have a question. So you mentioned that your work also extends to the flat initial condition. So what about other initial conditions? So non-flat and non-narrow wedge?
It's also maybe also possible to do with the Brownian motion. So you start the KPZ equation from the Brownian initial data, but the key like behind like the proof is really like, as I mentioned, you really need to understand like what is this rho star. So this rho star really comes from the physics heuristic, which corresponds to solve a pair of PD at here. So this pair of PD, like it has certain boundary condition. And so in the case of like KPZ starting from narrow wedge or the KPZ starting from this flat initial condition, you can find out like one solution, this rho star, which is becomes the input of our rigorous proof. But like presumably if you can find out like other rho star, like if you start from other kind of initial condition, like this method of proof should also work. But I'm not sure like you can find out this rho star like for general class of initial condition.
Okay, I see.
Thank you. This rho star, this was the physics literature already founded, or this was the
So like this rho star like was recorded like in the physics work by Kamenev, Meerson, and Sasorov. Yeah.
I have another question regarding your early on. It's more of a remark regarding your early on physics intuition of explaining the large deviation. It's not really physics, heuristics about doing the large deviation. But I forgot where's your slide where you write down the,
like you mean this? Yeah, like so, yeah. Go ahead.
Yeah, so the meaning of this equation can be made rigorous without using distribution theory. You see, this is this. So if you equalize your right part, make it equal to a variable called you call it the rho. So
okay,
rho is L2, the right one, the next line.
Yeah.
So so there's a L2 viscosity solution theory. There's in general LP viscosity solution theory. So if you have a Laplace operator here, like it's going to work. It's essentially using this Laplace operator, which is the linear part plus the square of the gradient. So so there's a so you cannot use maximum principle, which is L infinity based, but this is a monotonicity operator. You are using monotone operator, and there should be an L2 theory. So this whole thing, without going to the stochastic heat equation, you should still have a proof. I believe you don't have to use the chaos expansion. That's what.
Like you mean to obtain a large deviation for the KPZ equation, right?
Yeah. Is to renormalize and then.
Yeah. like I agree. For example, you can also use the theory of regularity structure like to deal with that.
Yeah, but the regularity structure doesn't use the viscosity solution. What I mean is you can just simply use viscosity solution for your large deviation. It's simpler than the making sense of the stochastic PDE, because you are talking about deterministic equation, your right equation, the right one.
Okay.
Yeah. So
Okay.
so you can you don't have to convert it to SHE and do this change of measure kind of thing.
Okay, I see. Thanks.
Further questions? I have one more question. So
Yeah,
can you
sure.
also get some sort of a law of the iterated logarithm?
Actually, yeah. Like you mean for the KPZ equation?
Yeah, so around 0.
Yeah, like, so presumably you have the large deviation. Okay, actually, I think the law of iterated logarithm is more related to the moderate deviation, right? Yeah, but presumably, like, you should expect you can also get law of iterated logarithm,
yeah.
like once you have the characterization of the large deviation. Yeah, but like I'm not 100% sure. Like it's just a direct consequence. And I think like you may need more ingredients.
Okay. Further questions?
I do want to add one comment regarding the previous question.
Yeah.
So it is true that the PDE for large deviation can be posted at level KPZ. I guess the point here is that analyzing the deep lower tail PDE limit of that object is hard because of this viscosity transition. And the real reason that we're working with SHE is because we found a way to do that part of the argument using SHE, and that prompted us to do large deviation at level as SHE. And it is totally true that we could have done it for KPZ as well.
Yeah.
So I missed that comment. So so the calculus variation, once you get, there are two levels of the problem. One is to get the large deviation, forget it. So there are various ways. So once your emphasis is the calculus variation problem is of course, is the main concern here.
The limit of that.
So
the limit,
like,
of course,
like this 5/2, like we're taking the limit.
Is the PDE on PDEs. So you are reducing the dimension by taking the limit. So so how do you see the difference of working with like either the HJB equation directly versus the stochastic heat or the heat equation, perturbed heat equation at that level in the calculus variation? And
I mean, in a sense, it's like we're working for HJB equation, but using this variational formula. So there are different ways to work with Hamilton-Jacobi equation. I'm referring to inviscid one without viscosity. One is you work with PD. The other one is you can write it as a variational formula using.
You always have the viscosity here for this problem, right?
What's that?
You always have the viscosity for your problem here.
So in the case, in the limit when lambda goes infinity, it looks as if you are having an inviscid equation. That's what we're dealing with, actually. So in the region, in the deep lower tail region, the PD turns into inviscid equation.
Okay.
And essentially, we're working with
I see.
The Hopf-Cole, variational formulation of the inviscid equation.
So okay, but then that's even more says it should be viewed from the maximum principle kind of thing.
Yeah.
So it's so you are going from LP solution to L infinity solution in the limit.
Yeah, that's true. Yes.
Oh. Thank you.
Thanks.
Okay. Are there still is there still a final question left? If not, let's thank Yier again for this very nice presentation.
Thanks for your attention.
And we will meet again next week, Friday. for the next seminar. Okay, see you. Bye-bye.
Bye-bye.